Picture thick engine oil dragging across a flat metal plate. Now, think about warm air blasting against the icy inside of an automobile windshield, or cool room temperature air solidifying a moving sheet of hot industrial plastic. This schematic diagram shows the core variables common to all these systems. Even though fluids and materials change, they are structurally identical. We evaluate the free stream temperature, the velocity of the flow, surface area, surface temperature, and physical length. Because the structure is identical, we use a standardized 5-step framework to solve all of them. This permanently eliminates the confusion of guessing which textbook equation you are supposed to use next. To follow along and execute this process yourself, you only need 2 things on your desk: the thermodynamic property tables for the specific fluid you are working with, and a calculator. Mastering this single sequence shifts your role completely. You stop memorizing a chaotic list of formulas. Instead, you simply execute a predictable, logical checklist. Step 1 is finding the film temperature. The fluid next to a hot plate is warmer than the free-flowing air miles away. You cannot base fluid properties on just the hot surface or the cold free-stream air. You need the average boundary temperature. This property section averages the 20 and 60 degree temperatures for a 40 degree film temperature, where we pull fluid properties. Continuing down, Step 2 calculates the Reynolds number, a mandatory traffic controller indicating whether fluid movement is smooth or highly chaotic. By taking that calculated Reynolds number and comparing it against a known critical threshold, often 5 times 10 to the 5th for a flat plate, we determine whether our flow is strictly laminar or if it has transitioned into a combined flow condition. In this second analysis block, we see an outcome where the flow crosses that threshold. Because the calculated Reynolds number falls between 5 times 10 to the 5th and 10 to the 7th, we have a mixed condition of combined laminar and turbulent flow. This is the ultimate gatekeeper for formula selection. Skipping or miscalculating this Reynolds check guarantees absolute failure on the very next step. Step 3 is determining the Nusselt number. You can think of this as a heat transfer multiplier, and you choose your equation directly based on the traffic result from Step 2. This block calculates the Nusselt value using our Reynolds and Prandtl numbers. Step 4 converts this dimensionless number to reality, the convection coefficient, H. Using the isolation formula here, we multiply Nusselt by thermal conductivity and divide by plate length. This coefficient is the critical bridging metric. It is the required translation between the raw fluid dynamic data we've gathered and the actual thermal energy transfer we want to measure. Step 5 is application. We take that physical coefficient and plug it directly into Newton's law of cooling to find the final rate of heat transfer, or into our drag force equations to find the physical force acting on the surface. However, you must watch out for the hidden danger of thermal radiation. When you are dealing with high-temperature materials, convection is entirely insufficient to describe the total cooling happening on the surface. This schematic of a plastic sheet illustrates a scenario where both cooling forces act on the object simultaneously. An accurate energy balance here must sum the heat lost via convection with the heat lost via radiation to find the true answer. Correctly applying this final step requires looking at the real-world physical context of the problem. An engineer cannot afford to blindly trust incomplete math. Review the logic. Film temperature dictates your properties. The flow dynamics give you a Reynolds number. That dictates the Nusselt equation, which converts to your coefficient, allowing you to solve for the final target. By holding strictly to this sequence, you ensure you will never get lost halfway through a flat plate convection problem again. What is truly remarkable is that this exact sequence functions perfectly for complex geometric shapes like cylinders and spheres. The only variable that changes is swapping out the specific textbook formula you use in Step 3. Engineering intuition comes from trusting a structured process. By standardizing the steps, you free your mind to focus on the real physics, rather than fighting the formulas.